Hello, chemists. Jolly again. Let's do question number 4 of that multi-spectra workout. Alright, so here is question number 4. Alright, first thing I'm going to do is count those peaks. A, B, C, D, E, and F. So 1, 2, 3, 4, 5. Looks like I've got 6 peaks. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 6. So that's 16 hydrogens, which means there's no nitrogen or halogens in there. Let me count that again. 6, 9, 10, 11, 12, 13, 14, 15, and 16. All right, and then let's start putting some numbers and some splitting patterns. All right, let's start with this one at 5. I'm just not sure. I'm seeing maybe a hint of a quartet in there. Just maybe a hint of a quartet, but I'm not sure it's going to be, so I'm just going to say multiplet on that one, although there's kind of a hint. Well, that's definitely a multiplet, and that's definitely a multiplet. That looks like a doublet. This one looks like a doublet, and that one looks like a triplet. All right, so for A, where does it land? Oh, about 4.9. So I have got a multiplet that integrates for 1 hydrogen at 4.9. Now, 4.9 is not a very common number in our proton NMRs, so that means something really crazy is going on. It's very shifted. It's next to 2 things, but it means something special. All right, I have a 2. We'll say 2. So we've got B is a multiplet for 1 hydrogen at 2.2. We've got a multiplet for, whoops, not what I meant to do. We have got a multiplet that integrates for 2 hydrogens at about 1.4. And then we've got this nice doublet that integrates for 6 hydrogens. And that is at, I don't know, we'll say 1.2. And then it looks like we've got another doublet that integrates for 3 hydrogens at, we'll say 1.1. And then finally we've got a triplet that integrates for 3 hydrogens. We'll say 0.9. All right, let's go back and do some interpretation. Now again, this 1 hydrogen. Okay, so there's my 1 hydrogen, but it has shifted a lot. It has shifted a lot. So I'm going to put a little asterisk note to myself. It's next to somebody that's pulling on it. All right, this multiplet at 2.2, well, I like the number. It says to me it's next to somebody sp2, so next to a benzene, next to an alkene, next to carbonyl. Now this is the alkene world. Okay, this is the alkene world. So I'm going to put this. All right, a multiplet for 2. Well, I know that has to be a CH2, but it doesn't really help me telling me what's on the sides of it. Now this one though, a doublet that integrates for 6, that screams this. Whoops, let's make CH3, CH, CH3. All right, that screams isopropyl group. Okay, a doublet integrating for 6 is just screaming that I am an isopropyl group. A doublet for 3 hydrogens means I'm only next to 1 neighbor. And a triplet for 3 hydrogens means it has to be next to a CH2 group. All right, so there's my pieces. Okay, there's my pieces. Now again, if this was all I was given, I would now start putting those pieces together and use maybe my multiplets to help. But I have lots of other spectra, so since there's so many pieces, I'm going to keep going. All right, A, B, C, D, E, F, and G. So there's 1, 2, 3, 4, 5, 6. So there's 7 peaks. So there's 7 unique carbons. And right now, that confirms that there is a carbonyl. So up here in my proton NMR, I just confirmed that it's probably that one. All right, these are just my sp3s, nothing of interest there for me. But this area, it means it's connected to something that has made it shifted. All right, Now again, I could start nitpicking numbers right here. So that looks like it's about 177 ppm. I could go to my carbon 13 chart and I could see, is that an ester range? Is that a ketone range? I find them very broad, so unless I have to, I use it just as my secondary proof. So I'm going to go on to my IR. Oh yeah, those are beautiful sp3s. Oh look, that's a beautiful carbonyl. Now my eyes are looking right here. Okay, so this region about right here, that's where your carbon or your carbon-oxygen single bond would go. And those are pretty dominant, but they're not down there. So I'm just going to put a CO question mark. A CO question mark. So if I'm wrong, I will come and erase that on one that I was going to turn in. And if I'm not, I would come and erase the question mark. So right now, it looks like either a ketone or an ester, because this peak right here doesn't have that beautiful peak that we've seen in aldehydes before. So that doesn't look like an aldehyde to me. I won't cry if it turns out to be one, but it just doesn't have that look to it. All right, molecular weight of 144. Now notice it was so tiny that I had to tell you that it was down there. So we're not going to get much information out of that. So it's a good thing I had it written up here. So 144 AMU means it's even, so there is no nitrogen. And I do know there's at least one oxygen. Okay, I know for sure there's at least one oxygen. So I'm going to go 144 AMU minus 16 is going to leave me, getting my calculator, 128. All right, so I would have to put everything together with 128. Now, I thought maybe there was an ester. So I'm going to subtract 32 over here. For 2 oxygens, I'm going to get 112. All right, if I only do 1, let me see. So how many carbons could I do in there? That is an awful lot of carbons. I'm actually going to go to the smaller number here. I'm going to go to the smaller number, and 112. Let's do 8 carbons. 8 times is 96. So 112 minus 96 is 16 hydrogens. Okay, that seems reasonable to me. So C8H16O2. Alright, so 2 times 8 plus 2 is 18 minus 16 is 2 over 2. That is 1 pi or 1 ring. And I already know there's a carbonyl. So I know that one's good. All right, so I like that, but I'm going to go back and check just in case there's only 1 oxygen. All right, so 128, let's do 9 carbons. All right, so 9 carbons, 9 times 12. If I did that right. And that's going to leave us 20 hydrogens. All right, that's not looking so bad either. C9H20O. All right, let's check that one. 2 times 9 plus 2 is equal to 18, 19, 20. I already know this is not correct because I know there is a carbonyl. Okay, because I know there's a carbonyl. And this is telling me there are no units of unsaturation, so this is the better formula. All right, C8H16O2, and I also knew that there were 16 hydrogens in that formula, and guess what? 16 hydrogens is what the proton NMR showed me. So I already forgot, C8H16O2. C8H16O2. I'm going to write that right here. C8H16O2. All right, that means I have an ester. All right, this right here would show that I have an ester. That would show that I have an ester. And I need it to be sandwiched. Remember I told you this 4.9? That is really downfield. So I think it's probably sandwiched on both sides, and the only way in this molecule to sandwich on both sides is to put a CH right there, and maybe put an O right there. Put an O right there. Alright. So I just used, okay, I should use a different color here. Let's use red. Alright, so I just used this one, and I just used this one, okay? I put them together. So there's one of them, and there's one of them. Alright, this one is the one that I think is at 4.9. It's sandwiched in between the carbonyl and that oxygen. Well, let's go down here to my triplet and my doublet down in the 0.9 and the 1.1 region. I know there's a CH3CH2 somewhere, and I know there is a CH3CH somewhere, and then I know there is an isopropyl somewhere. Alright, so I have to get all of those pieces actually together, and right now I'm just going to start putting pieces, okay? Alright, now I know that there's a CH right there, so I'm going to put CH3, so there's my isopropyl. There's my isopropyl, so 1, 2, 3, 4, 5. I've taken care of 5 of the carbons, and that leaves me 3 carbons to go, and there's 8 total, so 1, 2, 3. Alright, so that looks viable at the moment, but now I need to check and make sure that everything matches. So there's 6, 7, 8. Oh, look right here, look right here. That can't just be hanging out all by itself. So is there anything that I think is a CH3CH? Do you see that right there? So I should put one of those right there, which would erase that, and I would just get one CH3. Alright, so do I have a multiplet for one hydrogen somewhere about 4.9? So this would be a 1, 2, 3, 4. Oh, that would be a quartet. And remember, I was talking about that kind of had the symmetry of a quartet. So a quartet at 1 hydrogen and somewhere greater than, I would usually say greater than 3 to 4 if I was predicting it. Alright, I also have a doublet. Well, not a doublet, a multiplet that integrates for 1 hydrogen, somewhere between 3 and 4. Okay. I have a doublet that integrates for 6, somewhere between 1 and 2. Go over here. I have a 1, 2, 3, 4. I have a quartet that integrates for 2, somewhere between 2 and 3. And then I have a 1, 2, 3. I have a triplet that integrates for 3, somewhere between 0 and 1. And so let's double check. Do I have a multiplet for 1 somewhere between 5 and 9? Yes, I do. Do I have a multiplet that integrates for 1 around 2.2? Interesting, interesting. I'm seeing that this one right here is not this one. So my multiplet for 1 hydrogen should be that one. It should be that one. Okay, so right now that piece is not matching for me. Do I have a multiplet for 2 hydrogens around 1.4? I don't have a multiplet for 2 hydrogens around 1.4. Alright, now this isn't necessarily a wrong molecule, but do you see when I was working backwards, it is not fitting all the pieces. It is not fitting all the pieces. So, we go back. Try not to fall in love with things that we've done. We have to keep an open mind. I know that there's 7. There is 7 unique carbons, so the only symmetry is with that isopropyl, so the others have to be just matched in. Wow, that's taking a long time to erase. There we go. Alright, let's go back to blue. Okay, So the piece that was really bothering me was that multiplet for one hydrogen at 2.2. So I'm going to start with that one. So, alright, so there's my multiplet that integrates for one hydrogen. Now, how am I going to make that a multiplet? Well, that is a very interesting question, because I need to put two things onto it. Alright, so I need to put something there, and I need to put something there. Alright, now, I'm also going back to this 4.9. Over here, I needed something that was very, very downfield shifted. So I'm going to put a CH, and I'm going to put the O. Now, it's not an ester, but I'm trying to stay true to that really far shift. Alright, so I've got a CH with a CH3, so I should have a quartet that integrates for 1, somewhere between, greater than 3 to 4. Alright, so far so good. How about somebody next to this oxygen? Who should be next to that oxygen? Well, if it's going to be next to the oxygen, it's going to be really far downfield. Alright, let's try and put these pieces together. I know I have an isopropyl, and I have a CH, so I guess I better end that one. And then I have a CH2, CH3 that I need. Alright, now let's check. Oh, and we can't have just a little old oxygen hanging out there. So 3, 4, 6, 13. So I am missing a CH3. Uh-oh, I already know. That should be a singlet that integrates for hydrogen, and I do not have a singlet that integrates for hydrogen. Okay, so what is going on right here? What is going on? I'm getting really flubbed up with my multiplet at 1 hydrogen. They're around 5. Okay. I like this piece over here, though. I like this piece over here because this one should be a triplet that integrates for 3, somewhere between 0 and 1. This one should be a 1, 2, 3, 4. That one should be a multiplet that integrates for 2, somewhere between 1 and 2. This one should be a 1, 2, 3, 4, 5. That should be a multiplet that integrates for 1, around 2 to 3. Okay, that's the one that I was going for B. And this one should be a doublet that integrates for 3, somewhere, I don't know, 1 to 2. Okay, I'm liking all of those are matching up. So the problem I'm having is over here. And I don't have an isopropyl group. Alright, so I'm going to change. And I'm going to put, alright, an oxygen next to a CH next to my isopropyl. Now let's see what I should expect in my proton NMR. Alright, I should expect a doublet that integrates for 6, somewhere between 0 and 1 or 0 and 2, and then I should see a multiplet that integrates for 1. Now this is the part that I'm going to have to live with. That should only be between 3 and 4. That should only be between 3 and 4. Other words, that 5 that I have, okay, could it happen? Absolutely. It's one of those things that you choose one piece and sometimes it leads you down a crazy road. All right, but this matches everything that I have in the proton NMR. So let's put some letters to go along with it. What color? Let's use purple. All right, so A, I believe to be this one. B, I believe to be that one. C is the 2 hydrogens. D is the doublet for 6 hydrogens. Let's see, I said D. E is the doublet for 3 hydrogens. And F is a triplet for 3 hydrogens. Alright, actually, those all lined up very nicely, even though that shift didn't quite go the way I'd hoped. back to blue. And let's go down to our carbon 13. So we have a CH3, CH, CH3, O, C double bond O, CH, CH3, CH2, CH3. All right, well, this is definitely A right there. B will be my next furthest down field, so I believe that one's going to be that one. C would be my next furthest down field, so I would bet on that one. All right, now here, D, E, F, and G. Well, all right, let's take a stab at it. I think closer to the oxygen should be the next one. So let me see, A, B, C, so D. So I believe these are going to be D, and then E, and let me see, I missed somebody. E, and now, as odd as this is, the G is the smallest. The G is the smallest. So I'm actually going to change this to G, and then I'm going to change this one to E, and that one to F. Only because I went on that height. Now remember, never go on height unless it's a tiebreaker, and all 4 of those, I didn't know where they fell, so I used it as a tiebreaker. All right, that matches my carbon 13 NMR as well. All right, does it match my IR? Yep. And so it did turn out to be an ester, and it did turn out to be C8H16O2. All right. There is only one piece that really, really, really didn't jive up, and that was this one right here. Okay. So that shift of 4.9 could be because it's sandwiched between an isopropyl and the oxygen. So again, that was the only one that really didn't jive to our very standard numbers. All right, and that's how you would go through a more complicated one, but notice I didn't start with the proton NMR. I kind of had to have the information from all the pieces. All right, until next time, Jolly out.